Let's continue this tutorial on Nars. So last week we have covered the first layer with a kind of complete description about the language, the inference rules, and the implementation. Then, as I mentioned at the very beginning, the whole system contains 9 layers in the current design. The layer 1 only gives you the very basic. So let's see, what does the layer 1 already implement or provide and what it doesn't. What it gives us is the fundamental, right? A basic term-oriented language, semantics, stochastic inference rules, and control mechanism and memory structure. They're all designed according to the assumption of insufficient knowledge and resource. So that's the foundation of the whole thing. Then what is missing? Well, clearly everyone can see. Right, all the domain knowledge are described by a subject-predicate sentence with inheritance copular plus a truth value. Clearly, that's far from enough for a lot of practical application, not to mention to provide general intelligence. So all the other layers on top of that, in a sense, attempts to extend this part. Okay. On the other hand, the truth value basically remains the same all the way from the foundation to the top layer. Okay. So now let's see what we can do about this. Basically, in the following, let's see, we are going to introduce 3 copulars. So overall, there are 4 copulars in the system. Okay. So that's relatively either. On the other hand, for this and this, I said that in the system, subject and predicate are kind of like treated the same way. Okay. So they're all terms. So in the following, actually, most of the work is to extend the concept of term by introducing internal structure. Okay. Previously, we have mentioned the term basically is just an internal data structure. Okay. In the first layer is nothing but a single ID. You use the ID to name an internal data structure. And then we're going to allow all kind of like more complicated data structure. So the system's expressing power will be increased so that it can represent more complicated knowledge. Furthermore, related to it is inference rules need to be extended to handle the new structure. Okay, so that's kind of like the big picture from here all the way to this. Since we only have 3 lectures left, 1 this morning and 2 tomorrow morning and afternoon, for the other layers, we are not going to have the time to go into the detail compared to the first one. Okay, but I will give you the basic idea. All the details you can find it in the book. Okay. So, and also we are going to kind of like group the above layers into 3 categories. So today we are going to talk about level or layer 2 to 4, which the idea is to introduce a compound terms. And also the basic intuition for all of the 3 layers come from the same place, that is set theory. Okay. So it's kind of like use the idea from set theory to extend the concept of term in various ways. Okay. But the accurate definition, the treatment is not the same as in set theory, as you can see. First, layer 2. Here I call it derivative copulars. So we are going to introduce 4 new copulars on the base of inheritance copula. Okay. But this 3 are kind of like pseudo or virtual. Later you will see it's not really implemented, but we conceptually introduced. And this will be the thing that's really implemented together with inheritance. So the definition, we will need to use the formulas in the book. First, this similarity copular is the kind of like most straightforward thing you can do in this structure. That is, it's nothing but symmetric version of inheritance. And this one we already know from the very beginning that is directional, right? From S to P, from P to S, you can write both of them, but usually they don't have the same truth value. Also, they have different scope of evidence and so on. Okay. Then, if you write it in this way, in this system, okay, they will be handled as the same because similarity is defined as two-way inheritance, as you can see here. Okay. The similarity copular is defined by S is similar to P if and only if there is an inheritance in this direction and in this direction. Okay? Also, by the way, all those extensions from one level to this level, accurately speaking, is done in 2 steps. First, we mentioned this one, also we have seen that last week. Start from this, right? We introduce a binary logic first, right? Then we add uncertainty into it to turn it into non-axiomatic logic. Then to build on top of that, accurately speaking, is the extension doesn't happen in this way. Okay, that's not what actually happened. The actual picture is something like this. I first extend this binary logic into a more complicated one by adding more grammar rules and more inference rules. Okay? Then I add uncertainty into that, okay, to make it non-axiomatic. Okay? That's a better, more accurate picture for this and also for all the levels. So each time you see that we are going to expand this binary version by adding more grammar rules and inference rules. And then we do it in this way instead of doing this. This picture also shows you why we want a separate binary logic system, even though that one is not based on the assumption of insufficient knowledge and resource, which is the key of the whole thing. Okay. Then hopefully at the end you can appreciate the simplicity and solidness of this approach by doing this first. So what I'm talking about right now is this step. Okay, you see there's no uncertainty. There's no uncertainty. Everything is either true or false. So in this binary logic, we introduce this copular using this tool. You see that once again I'm using predicate calculus as a meta language, so I can use this symbol and this symbol. And these 2 symbols in this context is not part of Nars, but part of predicate calculus. Okay? I'm using predicate calculus to define new structure in Nars. So this one is equivalent to this way and this way together. That's pretty easy to understand. And now we see, we already said the inheritance relation is defined to be symmetric, to be reflexive and transitive. Okay. It's neither symmetric nor anti-symmetric. That is, from this one, you don't know whether this is true or not. Okay. It can be either way. Okay. But now this one, by definition is reflexive, symmetric, and transitive. Okay. So everything is similar to itself. If A is similar to B, then B is similar to A. Then if A is similar to B, B is similar to C, then A is similar to C. Well, of course. But some people say, oh, similarity is not always symmetric. Actually, in psychology, some people actually introduce the distinction, say that some similarity is symmetric, some are not. Okay. I know that kind of convention, but in this context, whenever we say similarity, we mean symmetric similarity. Actually, those people who are talking about asymmetric similarity, that's in this system actually is handled as the inheritance. Okay, so we don't need to make that distinction. So this becomes a matter of definition, and this is always true. And by the way, so this two will be handled as the same, and within the implementation, of course, you don't want to keep both of them, which will be confusing. So in the implementation, if you try the demo, you will see that whenever this is a situation, we're not going to have this one. We're going to have this one because I'm going to simply sort, okay, the subject and predicate so that alphabetically the smaller one is always put in the first, so it's unified in the code. So you should not be surprised if you try to put this into the system. You will see you can type that in the input window, but you click OK in the display in the main window. You'll see this two will be switched. Okay, just because within the system, it will just always keep the same format for similarity. For inheritance, of course, that's not going to happen because the other way around is a different statement. So that's a little bit of detail about similarity. And also what many other things will become straightforward. Of course, if you know that it goes in both directions, of course, you can derive it go this direction and that direction. So if you have both of them, you can just write one sentence. Also, you'll see that if they're similar, then S is in both the extension and intension of P, and P is in both the extension of intension of S. That's straightforward to prove. And also, the two will have the same extension and same intention. What that mean? It means in this system, by definition, they will have the same meaning, right? Meaning is nothing but the extension and intention. That's, again, consistent with our intuitive usage of the term. Okay? So similarity in the extreme form, meaning that if it's completely true or false, actually the similarity is nothing but the identity. So these two things will be handled as identical. Okay? So you'll see also the definition gave you a whole bunch of inference rules. Some of them take one premise to get the conclusion. Some of them take two premises to get the conclusion. It's pretty easy to get. Question? Yeah?
If you get evidence for an inheritance relation with one of the similar terms, how do you know if you should apply it to both or just to one so that you're different?
We are not there yet. Okay. As soon as you talk about evidence, we're on this side. So it's not taken as binary. Yes, that's a key problem about similarity. Later we will see. Okay. But here now we are talking about a pure binary true or false situation. So at the moment we don't have that issue, but later we'll see how to handle that. So yeah, we are going to start the discussion by talking about, instead of talking about how the evidence transform from one to the other, let's first define what's the evidence for this one by itself. Okay. You see, that's quite natural to say that since this one is a summary of this, so the evidence, the positive evidence of this one will be the positive evidence of either of the two, and the negative evidence of this one will be also the negative evidence of either of the two inheritance relations. Okay? Which directly give you this consequence. because we already know that the positive evidence of this and this are the same. Right? Last week I explained that a lot. So that's the same thing will become positive evidence of this. That is no surprise, the common extension and intension. But negative evidence is a different story. Last week we say that negative evidence of this one and this one are different. Okay? But both of them will provide negative evidence for the similarity. Okay? That is, you see that this one actually have a larger, kind of like a larger evidence base in terms of negative evidence. So intuitively speaking, let's see if we are evaluating all those three together. Okay, the last one actually is the same as this. So based on the same evidence. So they are going to have the same positive evidence, but this one will always have more negative evidence than the other. And then we'll see what I mean. Anyway, that's the definition. And then, now that's really talking about uncertainty. Okay, how to do inference? Then we have a stochastic rules format. Then in this one, you see in this one we have a 2x2 matrix because we have inheritance in both directions, so there are 4 combinations. This one there is just 3x3. Why? Because we still have the old one. That is, 2 of the premises are inheritance relation. But in this case now, the conclusion can be similarity. And also, what if one of the premises is the similarity itself? Then we need new rules. Okay? So you see whatever we already covered in the first layer, we are now going to repeat it in this table, so that, for example, this one actually gave you deduction, but that's already covered, right? So here I only mention the new things to be introduced in the second layer. So altogether, you see that there are 7 possible results, but correspond to 3 inference rules. Okay. The others are just a different order and so on of the same rule. Let's see them one by one. The first case is here and here. Okay. That's what I call comparison. Comparison is the inference by definition in this system, of course, where you have 2 inheritance relations as premise, and then you get a similarity as a conclusion. The intuitive idea is actually pretty simple. That is, if kind of like A and B, okay, have the same relation with a C, then A and B are similar to each other, right? With respect to that. But once again, you see the premise only gave you some evidence, as I said before. It's not a conclusive proof of anything, right? So you have reason to believe they're similar to each other. And you see why there are 2 cases that directly come from the symmetry between extension and intension. So you see here is M is in the extension of both S and P, which support the similarity between S and P to a degree. And in this case, M is in the intension of both S and P, which also support S and P are similar to each other to a degree. And so this thing is built exactly like how we build the induction and abduction rule. It's just in those 2 cases, the result is one way. In this case, the result goes in both directions. Okay? So some of you may ask, if I really see this one is premise, will the system do a induction or do a comparison? Well, in the current implementation, I will do both. That's why I said that very often from the same pair of premise, you get more than one rule which is applicable. Okay, in that case, they will actually apply both of them, then get a result. So now, for now, you can see that just from this pattern, let me just ignore the truth value. In the current implementation, you actually get all 3 of them. Okay, this are two induction in different direction. This is a comparison. And they may or may not have the same truth value. It depends on the truth value of this one. Okay. So that's this. And also, the truth value function comes directly from, again, using the same way. Again, treat everything as a binary and try to build a Boolean relationship, then extend that Boolean relationship into real number using the functions we introduced last week. Okay? So you see, in what case you have positive evidence, then that happens when all of them, all the premises have positive claim, right? So you have 1, 1, 1, 1, then you have positive. In one situation, you have evidence, either positive or negative. Then at least one of them need to be positive. Okay? You see that if we say M is P, M is not S, then what? Then with respect to that, these two are not similar, right? So that's negative evidence for the conclusion. But on the other hand, if both of them are negative, if M is neither this nor this, there's no evidence at all. It have nothing to do with the conclusion. Okay? So that's why we have an or here. On the other hand, still this one need to be fully confident for the conclusion to be obtained. So later you may want to compare this function with the, say, induction and abduction function. See their similarity and difference. And then what? And the other case is perfectly symmetric. When you're talking about intension, once again, it's basically the same thing. Okay? So it's actually the same function. You see that this one is symmetric with respect to which one is the first, which one is the second. It doesn't really matter. Okay? But for induction and abduction, it matters. For comparison, you see it's symmetric. So that's one rule, which is in this table here and here. Okay? How to turn inheritance into similarity. Then we have this one, this one, and this one, and this one. That is what I call analogy in this picture. Okay. In general, analogy is another word which means many different things in many different systems or discussion. So this rule clearly only handle one very special, which I believe to be the simplest situation. Okay. Then later, if we have the time, we can talk about how to turn other form of what we usually call analogy into this format. Okay. So here, I just want to make it clear that we only handle one special situation. Which situation I believe is the basic. That is, if you already know these two things are similar to each other, what that mean? That means usually you can use one as the other, right? They're similar. So that means if you know the similarity, so analogy take a similarity relationship as one premise, and the other one is an inheritance, which indicates the property or instance of one of the two. Then what? Then the result is just that one replaced by the other one similar to it. Okay. So you see, if you know M is similar to P to a degree, and S is a M, then S is a P, just because they're similar. Well, not they are similar, okay, but this guy and this guy are similar. The same thing on the other direction. And here is, what if S and M are similar, then this is, and here you can replace M by S to get this one, M by S to get this one. Okay. The difference is, you see this function, if I say F prime, blah, 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 and that's the basic, basically is the same function as F, whatever is named, but exchange the subscript 1 and 2. Okay, you see that the difference is just which one is taken to be the first premise, which one is taken to be the second one. So they are actually the same function. So here you see, basically I always take the similarity to be the second premise, the inheritance to be the first one. If it's the other way around, like here, I just switch the order in the function, okay, instead of introducing another function. So the function itself is given here. Okay? If you compare it with the one we introduced in layer 1, you will see this one is very similar to the deduction rule. In what sense? In the sense that the upper bound of the confidence value is actually 1. Meaning, especially you see that if the two things in the second premise are perfectly similar to each other, then that means they're identical, right? Then you just have to identical substitution of the two, right? Then the other conclusion you see that if F2 and C2 both equal to 1, then this will just be F1, this will just be C1, as we expected. Okay? You just replace one name with the other. And of course, the truth value should remain the same because it's equivalent substitution. But in reality, of course, that will never happen. That will just happen as a limit. Usually, F1 and C1, F2 and C2 cannot, especially C2 cannot be perfectly, true. Cannot be 1. So it will be something less. Then, of course, as a result, this one will be less. And also, it depends more on the similarity. If these two things, as we said, are not similar at all, you'll see the confidence of the conclusion will be 0, even though all the confidence of the premise may be 1. Just if I and you are not similar to each other, then what property you have and what property I have nothing to do with each other. Okay? Be careful when we say have nothing to do with each other, and when we say they are the opposite of each other. That's not the same thing, right? If they're the opposite of each other, then that means you will do something about the frequency value. Okay. If they have nothing to do with each other, then the confidence value of the conclusion will be 0. And whenever the conclusion have a 0 as a confidence, if you think about the definition we introduced last time, frequency actually doesn't matter. Actually, it's undefined. Okay. You have no evidence. When you have no evidence, what's the percent of positive evidence? It's not a meaningful question anymore. Okay? So that's similarity, and you can also think about that. And finally, the last case in the table is the one in the corner. This one. This is nothing you see clearly. It's nothing but the transitivity of the similarity relation. Right? A is similar to B to a degree, B is similar to C to a degree, and A is similar to C to a degree. Actually, at the very beginning, I called this one deduction because it's very similar to what we usually call deduction. But previously, in layer 1, we already defined deduction as the transitivity of the inheritance relation. In similarity relation, later I realized the truth value relationship are actually not the same. So I introduced a new word just to separate the two. Probably not a very good choice, but I don't have anything better, so I call it the resemblance. So you see, it's basically the transitivity of the similarity relation, and the truth value function is this. You see here a key difference between this one and again, this is a strong form of inference. The confidence can be very close to 1. The key difference between this one and deduction is we already talked about this last week. That is, deduction you don't get a strong negative conclusion, right? In the rule we introduced before. But this one you can have a strong negative conclusion because of this OR factor. Okay? F1 and F2 doesn't need to be both to be 1. 1, 0 is okay. In that case, you see this will be 0. Okay? And this can still be very close to 1. So it can give you a very strong negative conclusion, which, as I actually already said before. So you see if A and B are very similar to each other, okay? And B and S are very different, then A and S will be judged to be very different. Okay? It's possible to have a strong negative conclusion. Other than that, you see, it's not that different. from deduction. So that's the three truth value functions introduced in layer 2. Okay. As I said, this one is more similar to induction and abduction. These two are more similar to deduction, but with a small difference. And in general, I call this group weak and call this group strong. The difference you see is in confidence. It's not in frequency. Yeah. So that basically handles similarity. Then we are going to introduce three other copular, as I said, that kind of like not really real. It's kind of conceptually implemented, but in reality, they will actually be translated into inheritance in the implementation. You don't really see them in the code. Okay. Where they come from the very, well, many of you may already thought about that. Inheritance copular, as I said, the intuition comes from set theory, this one. It's kind of like a subset. But now I can say more about what's the difference between the two. The difference, a key difference is in set theory, this one is defined pure extensionally. We are talking about whether A and B have common elements. We don't care about whether they have common property or anything like that. Okay? On the other hand, to me, this is crucial for this relation to be defined both extensionally or intentionally. That is, you can get evidence by looking for common instance. You can also looking for evidence for common property. What is the property? Well, in this case, this one contains the instance of this one contains the property of this one. So a clear situation, so the extensional part is similar to the intentional part, you see. If we have A both in B and C, again, let's start from the binary case. And then we know B and C have something in common, right? So the picture will be something like this. And CA will be somewhere here. So it gives you some evidence to believe, in some situation, B can be used as C, which is, not too bad. But the intentional situation is very different, which looks like this. Okay? In set theory, if you have A here, B here, C here, then can you use A as B? Well, in this picture, of course, completely no, right? There's no overlap whatsoever. But after I worked in this project for a couple of years, I realized that it's important in this kind of situation to allow some evidence to be given to this statement. Then I realized that to stay with set theory is not going to allow me to do that at all. Okay, that's why I keep saying that this have some intuition come from here, but they're not the same. Okay, and also whenever in the future when you write this, you're not supposed to write this picture as what it actually means, because this kind of Venn diagram only capture the extensional situation, not the intentional situation. So you need to remember that. But in the same process, we can still use this as a kind of a metaphor or a way to help you to understand. But that already raises the issue that is, we know from set theory, I assume all of you have taken set theory, you know this and this in set theory, they're not the same thing, right? Not the same thing at all. In this case, you have A, and this lowercase a, or let me use a different letter just to make it more clear, is one element. In the second situation, this is A, and this E is a subset, right? Clearly, they're not the same thing. And also, in natural language, the intuitive meaning of this is to be, right? Not in the sense of to be or not to be, but in the sense of something is something else. But again, we have this scenario and this scenario to be separated. For example, we have been using birds. Let's continue. Say we say swan is a type of bird, and we can say treaty. Again, that's a typical name used in AI literature for knowledge representation. But if you write that doesn't sound right. Because here you're not talking about a type of bird anymore. You're talking about that bird, a concrete instance of bird. Okay. So the way in sensory, you know that in sensory, actually this one is introduced as fundamental. This one is defined using this one, right? What is a subset? Check your sensory textbook. It will say that everything in A is also in B, right? And then that's actually the definition for A is a subset proper. It's just a subset of B. That's the definition. So this is taken to be fundamental. This is taken to be secondary or defined. But in this logic, I pretty soon realized that I have to do the other way around. Because all the inference rules, as you see in the first layer, it's introduced here. And also we can introduce this one as a primary relation by directly using is reflexivity and transitivity without talking about what is in it. Especially, I already mentioned that a term is not necessarily a set at all, okay? Which also introduce many, or I will say solve many traditional problems. For example, uncountable nouns. I already introduced that concept somewhere before, probably in a book. For example, how to say water is a type of liquid. In this system, it's pretty simple. In Nars, it's pretty simple. You just say, okay, water is a special type of liquid. Okay, but if you do it in this way, in traditional set series format, you will have to take water and liquid as a set, and then people will ask, what's the element in that set? You cannot count waters like you count birds. Okay, so this kind of definition is more suitable for countable nouns. It's kind of okay if you can ignore intention, especially. In that case, even you concentrate on extension only, and it will be weird for say math nouns or abstract nouns. Okay, how about how to say that? Human intelligence is a special type of intelligence. Can you take intelligence as a set, and what's the element here? So anyway, but we still need to somehow separate this one. And actually, you see in the system, I actually do it in two different ways. One way is I introduce a special copular. I will use a special copular to indicate this is taken to be some kind of a special thing rather than a kind of thing. So that's one way. Another way, equivalently, is the same trick played in set theory, but the other way around. That is, in set theory, you know, this and this, they're the same thing, right? So that's the equivalence I actually use in Nars. So whenever I have this, which intuitively corresponds to that, I will translate it in the user interface into this. Okay? So that is why in the system you never actually see this one. Even though it's allowed in the user interface, you can type that, and then you click OK, it's translated. Okay? Just to make things simple. From the very beginning, I realized that in this situation, I actually have three choices. One is to allow both representation, allow some redundancy, then translate them between each other. One is to stay with this one as the basic, to translate this into this, and then finally is the other way around. Now, currently, I'm accepting the last strategy because later we'll see this representation will also need to be used somewhere else, especially when you need to define you need to define a set anyway. Okay. Then I realized since I need a set anyway, I will keep this as the internal one, and this one is allowed in the user interface. I can actually allow both of them in the system, but just make more complicated implementation a little bit more complicated, and also redundancy in the memory. Okay. Until now, I haven't found a situation where I have to do both. So that's how this one is handled. And also that means a couple of things. Another good thing about this is you'll see that for this copular, even though I allow it conceptually, I do not need any inference rules, any new inference rules, because they are handled in this way. Okay? So the only thing new is that I will have to allow this whole thing to be taken as a node. And that's the very simple, or the simplest form of what I call a component or compound term. Okay? That is, a term is defined by something within it, which is another term plus a logical operator. I'm taking this as a logical operator, which basically turns this into this. Okay, the meaning are related, but not the same, of course, as in cell theory. Okay? So if you understand this, you should be able to have no problem to understand all these three. Okay? They're all handled in the same way. So this is the first one. The second one, at the very beginning, is introduced purely because I really, really want to make extension and intention symmetric to each other. Okay, whatever you can do on this side, you should be able to do on this side. Especially in the first layer, I already decide one key difference between my system and the traditional system is traditional system only handle about extension, as I show you in set theory. That's not the only case, also in many other models. Okay, instead, I want to handle both extension and intention. So which means whatever you want to do in extension, probably also want to do with intention. Okay, so at the very beginning, I will just introduce that just for pure elegance or formal symmetry. But later I realized, well, actually there is a natural interpretation for that kind of thing. Which is explained later here, which is I called a property copular. And by the way, this one I call it an instance copular, meaning that this one, the subject is an instance of the predicate. This one is called property copular because the predicate is the property of the subject, which corresponds to, let's see, this example. Apples are red. Okay. If you do it directly in this way, in the first layer, then you are going to say apple is red. But later I realized that doesn't really sound right, intuitively speaking, because even though this is not defined on natural language, there is a natural mapping that we take every term as some kind of a noun, right? Which can be either generalized or specialized. So it forms some kind of hierarchy, which is what this inheritance relation is supposed to mean. But if you draw that kind of picture, you will see, for example, here. That's the typical situation, right? You can go up to be more general, like animal, objects, or creatures. You can go down to be more specific, right? You can have different type of birds. But if you follow, also this is symmetric so that you can make inference based on that, right? So what we have done is based on this kind of intuitive ontology among the concepts. But we realize that this kind of thing provides special situation because intuitively speaking, the instance nodes provide kind of like the lowest level of this hierarchy. Okay, so then you have a Tweety. That's kind of like the most specialized situation. You cannot go further. You see, the formal definition actually say that if you want to go down, it will become identical to the original. That is, you cannot have a subset which is not empty if the set only contains one single element. That's the formal definition I use. Okay. So with proper nouns, you go to the bottom of the whole hierarchy. Then it brings me to think about what if I go all the way up, or whether I also am going to hit a ceiling, which is the most general term. Later I realized, yes, that's the adjectives. It's a single property. You cannot be more general than that. Okay? Like red. Then I introduce something called intentional set, so that it will turn red or bird. Well, let's say there's some kind of red bird, right? So red by itself is an adjective, is a term, but it's not a category. But red things clearly is a corresponding category, which is just like bird or the other stuff. So intuitively, this square bracket will turn red into red things. Okay, that's the meaning of this compound term. Mm-hmm.
But red is a color, right?
Yeah.
So color will be more general than red.
But that's a difference. That's a very good point. But if you say that, you see that that kind of thing intuitively is correct, but that relation is not transitive anymore. Bird, well, at least some bird are red. Red is a color, but bird is not a color. For the same thing, this relation is not transitive. Okay, A is an instance of B, B is an instance of C, then A is not an instance of C. That is why in this system, this relation is more general because this is the foundation of all the inference rules. It's transitive, even in the reverse direction. It's transitive to a degree. Okay? So you can use that as a foundation so that you see another very important intuition behind this system is to treat all inference as some kind of like substitution. You use one term or one concept as the other to a degree in a certain sense. That's a very different intuition compared to the traditional logic. Okay, traditional logic is completely truth functional, so the focus is on truth. From the truth of A, you derive truth of B, and you derive truth of C. Okay, here, the whole foundation is you can use A as B, as C, as C to a degree. Okay, these two pictures are related, but not the same at all. Okay, so because of that, we introduce this as I call extensional set. Okay, so they turn something into a set similar to the set theory by what? By specify what is in it, right? That's how you specify a set. And this kind of thing actually also happens in set theory. Okay, that is, you define a set by the common property of all its elements. Okay, so you define a set of red things by saying that everything in that are red. Okay, then you use this intentional property to check whether some instance extensional belong to the set or not. So that's what happened. That is, again, I define a property relation as a new copular, but within it is actually replaced by whenever you see this, you turn it into this. Okay. So it's not really implemented physically. And then finally, what if you have both? You want to talk about, say, treaty is yellow. Okay, here the subject is an extensional set, and the predicate is an intensional set. Right? That's what I have here. You see, if you really have this what I call instance property relation, then you just translate it in both directions on both sides into this. Okay. That's like in this example. And again, intuitively, I'm using this arrowhead with a circle on one end actually to show this picture. It's kind of like, you cannot go further in this direction, or you cannot go further in this direction. Okay. That's the bottom or top of your whole hierarchy. And then what if you say color is red is a color? That's actually a different hierarchy. It's related to it, but it's a different hierarchy. So between those two hierarchies, you don't have transitivity. So why? Well, once again, like you see, if you say bird is red, you write it this way. You say red is a color. That's something like this. Okay. Then you have some relation between this one and this one, but it's not the inheritance relation anymore. It's component relation.
Different terms, or is it one term but with this limitation, with this something like quantum? These two reds.
Later we will talk about that.
Different,
they are different terms. They're different terms. Okay. It's just this term have this term as one of its component. In this case, the only component. So later we're going to talk about construction in general. Okay, but now we just remember them. So this is different, and also treaty and treaty as a set are different. Okay. Even though they're related to each other, later we will see they play different roles in reasoning. So anyway, you see the new grammar rule of the second layer is we are going to introduce 3-4 copulars. But once again, in implementation, only this one is real. The other 3 will be translated, just only used in the user interface. And then for terms, we allow a term to be put within a pair of this curly brace or square brace to become another term. Okay. So that's basically everything about the second layer. And there is actually no real new inference rule, but there are some mapping rules you see on the user interface. That is how to translate one to the other from the outside into inside. Okay. Actually, in the current implementation, I only have one-way translation. Okay. From if you give me this, I will represent that as that. Okay. But I don't bother to translate the other way around when I do output, but it can be easily done. I just think it's probably not necessary. So conceptually speaking, this is two-way perfect translation between these two representations. Another couple of rules, I don't have the time to talk about the detail. So you'll see that's basically the second layer. You see, the key idea is the new copulars. So now conceptually we have 5 copulars. Only 2 of them are actually implemented. But when you talk about the logic itself, you don't care about implementation. You can say there are 5 of them. The only new inference rule is actually introduced for this one. As I said, comparison, analogy, and resemblance. Okay, because the other 3 are just translated. All of them into this one. So that's the second layer. Relatively simple one. Okay. Any question?
The question I asked earlier about if A and B are similar, and you get C is B. How do you know if C is also an A, or is C was the distinguishing feature between two?
From this one, how to get this or this?
No. If you have C similar to B, and you have some amount of evidence for this, right? And then you get A similar to B.
Good question. You know that this actually, the evidence of this actually comes either in this way or this way. When you are going back the other way around, how can you know that whether you can go here or you can go here, right? That's correct. You cannot. Because as soon as this is similar to the situation what we mentioned before, that extensional evidence and intentional evidence merge, right? After that, when you do inference, how can you know which is which you don't? Which causes some trouble. Okay? Because, for example, when you collect evidence, it actually comes from a pure extensional situation. But later, when you use it in intentional situation, you will get, you are going to make a mistake. Okay? But I have two answers to that. First, some of those errors are inevitable because the human beings do that all the time. A typical example is if you are familiar with psychological work of Tversky and Kahneman on human judgment and decision making. Okay, some of you may be familiar with that. That's a very influential work. Kahneman actually get the Nobel Prize for that related work. They find humans systematically make mistakes on certain judgments. Okay. Actually, according to my interpretation in this terminology, some of them exactly because of that. Okay. People typically use extensional evidence to make intentional judgment and the other way around. But my argument is that's inevitable, and usually the result is right, but sometimes the result is wrong. Okay. But you have to pay that price. We're going to probably go back to that topic later. The same thing happened here. If you want to judge similarity, sometimes you get evidence from this way or this way. But later when you merge them together, there's no way for you, unless you really remember the whole history of where each statement comes from, there's no way for you to tell which is which means sometimes you're going to get it wrong. Okay? So that's part of the story. Another part of the story is if it really becomes absolutely necessary to separate the two. In this case, you should actually stay with this one and this one rather than use this one. The same thing for the extension and intention distinction. In layer 6, we are going to see a way which purely talking about the extension, purely talking about intention. If it is really necessary, it can be done. It's just in a more complicated manner. You kind of like more carefully organize your evidence. You don't merge them together. Okay, so the result will be more reliable and less mistake, but on the other hand, more limited. It's just that in that case, you're not allowed to use extensional evidence for intention or something like this. You pay a price, you get a result. Okay, so in the system in general, both of them are allowed, and then it will be related to the control mechanism I mentioned last time. The control mechanism will do evaluation and make something have a higher priority, something have a lower priority. Okay, if some of the result, some of belief typically very often leads to a bad result, and then we use control mechanism to say that this thing is not, probably you should not use it that much. That related to another thing, that is why analogy and metaphor are rarely accepted in science and mathematics. You can use that as a metaphor. You can use it to give you an idea. But usually you cannot really argue your conclusion based on that kind of thing. Okay, you can explain. That's how I get this idea in the first place. Why? Because analogy and metaphor very often are wrong. Or lead you to the wrong direction, even though very often also they lead to the right direction. It's kind of like more flexible and also not very stable. Okay, that is why in that situation you should actually use this, because they are much more better defined and maintained. But merge them, which will allow you to do a lot of inference and go in all directions, because intuitively, I guess you know, to a degree, everything is similar to everything else. You really push hard. Okay. But on the other hand, this inheritance relation doesn't allow you that much flexibility. Okay. So anyway, we will surely go back to that topic. Now let's move to level 3. Level 3 is actually the place where we introduce the notion of compound term, even though they're already used in level 2 in some special case. So level 3, I begin to formally define what is a compound term. The idea itself is actually pretty simple. That is, whenever you have a compound term, which means you have a whole bunch of terms, which can either be simple or compound. Or simple, as we've seen before, it's just a name or an ID, okay? With no internal structure like bird or animal or swan or water or liquid or red and so on. But compound is you have one or more than one of them put together using a logical operator, or we call, in this case, I call them a term connector. Okay. So you see that we can say this is a special case. This is a component. The connector is this pair of square bracket, which even though it writes as two symbols, but logically you know it's just one concept, right? The same thing for this one. So this is a special case, but later we will have a more general case that is, they can typically be more than one components involved. Especially for set, later, pretty soon we're going to extend that into set so that you can have, that's how set is defined in set theory, right? You can have A, B, C, D as the instance of a set. And also, for the same reason, you can have P, Q, R. Well, lowercase, uppercase doesn't really matter. As the properties by an intentional set. Okay. So what we introduced is just a special case before with only one. But an interesting thing to remember is we don't have empty set defined at this layer. Okay. You don't have anything like that so far. Later we will. Okay. That's not allowed. At least at layer 3 and below. Okay. So you must have at least one component. So that's the concept. It's pretty simple, and also there are some conclusions. For example, we can talk about the syntactic complexity, meaning that how complicated a term is. So you see a single word complexity is 1, then compound, well, you just add the complexity of each term together and plus 1. It's kind of like you count how many symbols is in that name. Okay. And this clearly can be recursively defined into more than one layer. Okay. So after that definition in the system, it will begin to make sense to say this term is simpler than the other in terms of their syntax. Okay. This definition has nothing to do with semantics, that is, who is related to whom. That's a different story. Okay. So syntax, we can say that, and also some small things which is easy to understand. Usually in the system, I use both the prefix format and the infix format. That is, you can write the operator either between or before the thing, except special case like this one, that's actually around the property. But in the implementation, actually, I'm using this internally, okay, which is more consistent with computer format convention in general. So in a sense, actually, this one can be rewrite as this. It doesn't really matter. So this is taken as a single operator. And also there are some other just common properties that you can see. You can apply it one after another. You can define recursively. By define this operator is only between two components, but the component itself can be a compound. Blah 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 blah. In that way, you can define a structure with n components. And also you'll see for two structures, if all of their components are identical to each other and they're using the same connector, of course the two compounds are identical to each other. No surprise. But not necessarily the other way around. If you have two compounds which are identical, it doesn't mean their components are identical with respect to each other, which is again very intuitive. For example, later we're going to see this intersection. Well, if overall this one are equivalent, it doesn't mean A is equivalent to C and B is equivalent to D, right? But the other way around, if they are, then of course the overall structure will be equivalent to each other. So that's why this is a one-way relationship. Is the implication is not equivalence. Okay.
Excuse me. To clarify, in this connector is virtually this link between sets or elements.
We are going to actually depend on the connectors. We're going to introduce each of them. You will see they may have different logical property.
So this notion is this notion means that they are all connected transitively, or what?
No, they are not necessarily transitively. This is just say that these things are combined by this into a whole. Okay.
So a connector could be more than one link.
Usually it's actually more than one link. Also later we'll see sometimes that actually means a positive link, sometimes a negative link. So at this level, as I said, this is a pure syntactic structure. Okay. On the other hand, what kind of truthful value you have, that's a semantic relationship. That's something else. Okay. So anyway, where am I? Yeah, so that's the basic idea about compound. Then there are several types of compound, and each of them have a different property. When we talk about them, we will give you some better idea about the overall definition. So let's see, in the layer 3, I'm going to introduce two groups. One is called intersection. I already draw it here. Okay. So the intuitive idea is again, the idea comes from set theory, right? You have two sets and you have an intersection, which is another set. Here the problem is you have two terms. Then you can define a new term, which is a compound, to somehow summarize the meaning of the two. Okay. This thing come into the system as a necessity, and because of the assumption of insufficient resource, because in a sense what you want to keep in your system is not the raw experience itself. It's a summary of the experience. Okay? A summary typically takes less space and use less time to be processed. It's more compact. Okay. One way to do that is use this kind of structure. That is, if you see A and B appear kind of like in a sense together all the time, then you just use one term to address both of them. So that's something like this. You see what I call extensional intersection is if you have something which is in T1 and in T2 in the sense that it's in the extension of T1 and T2, then you say it's in the extension of a compound, which is called extensional intersection. Okay? So the intuition here is actually perfectly the same as in set theory. Okay? So if we draw, now we need to be careful. I already told you that you're not supposed to draw a Venn diagram. But sometimes you can, because you just want to make it very clear that you're only focusing on the extension. It's part of the story, okay? Under that condition, you can still do that. So you can have T1, you can have T2, okay? If you concentrate on the extension, which is nothing but a set, so you can have T1 here, T2 here, then whatever here, the common extension, right? Then you can define a compound term just to capture that part, which will be written as this. Intuitively speaking, this part, and formally that's that definition. Okay. So everything in this one, if and only if they both in this one and this one. Once again, is the previous picture I said, first we only concentrate on binary logic. Okay. Then let's see, what if is, this is a matter of degree, this is a matter of degree, how to decide the matter of degree. Okay. But first we talk about pure binary situations. And then there are a whole bunch of result which is parallel to set theory. Okay. But you cannot really say this. There is nothing new, it's just set theory. But because accurately speaking, there's still some difference here or there. But the intuition, yes, pretty much set theory. So you see how to say yellow bird is something like this, right? Yellow is an adjective. Then yellow within square bracket is yellow things. Yellow things and bird, you know what's the overlap? That's the thing that's is a bird and it's also yellow, right? So that's a compound like this. Then the symmetric situation. You see, if I want to use set theory terminology here, again, I should call it union, right? That is this. This is T1. This is T2. The union of T1 and T2, these two merge together, but they don't. Once again, I want to show the symmetric between intersection and union, which is the same as the relation between extension and intension. You'll see why that's the case. Because this picture, that's from a pure extensional point of view. From an intentional point of view is we're actually introducing something here. Okay, by the way, this is something here. Intuitively speaking, if we really want to draw a hierarchy, by definition, you know that this one have this property. This one is a special case of this and also a special case of this. What if you want a general case of this and a general case of that? Think about it, they actually is the union of the traditional, in the traditional set theory notation. Okay. It's a bigger category, which include both of the original, okay, or the primary, the premise sets. Okay. It's a bigger one. But if that's from pure extensional point of view, but from a pure intentional point of view, what kind of property do you have for this big thing? Well, it must be the property that owned by both of them, right? Then it can be the property of the whole thing. So if you concentrate on the property, then what you get actually is the intersection of the properties. So for example, this one is defined by a property ABC. And this one is defined by a property BCD. And then this whole thing is defined by property BC, right? If you want to cover all of them. So that's actually a result from traditional logic study. That is, in this kind of hierarchy, when the intention is getting smaller and smaller and smaller, the extension is getting bigger and bigger and bigger. The other way around. If the extension, you limit the extension, if you draw smaller and smaller circles, you can say more and more and more about this property because they are more concrete. Okay? So here, even though I define intention and extension differently from the current common practice, this one still keeps some many of the intuitions as the traditional terminology. That is why I can still validly, I believe, use those terminology, even if the accurate definitions are different. But what do you call extension and intention? Question?
Yeah. What about this special kind of sets like red in this square brackets? It can't go into this relation. And what should system do if we are trying to, if it should apply this relation to this kind of set?
I'm not sure I fully understand the question, but I hope some of the following discussions, especially when we talk about examples, may answer that question. Okay. If not, we can come back to this again. But because I'm kind of like have a lot of other stuff to cover before the break, I will try to move a little bit faster, and then we will come back to those issues. And then there are a whole bunch of formal results or theorems can be proved. I'm going to leave it for you. Once again, the intuition is very similar to set theory, even though the accurate definitions are not the same. So you'll see, I don't have a term union. What I call intentional intersection actually is extensional union. So we have two intersections. One is extensional intersection. One is intentional intersection. Similarly, we have two difference. It's called extensional difference and intentional difference. That's the idea comes from, once again, set theory. You know, in set theory, you take the difference between this set and this set. The result will be whatever in the first one, but not in the second one, right? So in this case, it will be A. Yeah, we can do the same thing here. So you should be able to follow that by yourself. So it's kind of like intersection. It's just the second component it need to be a negative one, and also this difference cannot take have to take exactly two components. Okay, more than two is undefined. What if you really want to do this? Well, you have to use you use parentheses to decide, you know, what's the order. So this and this are different. Okay? They're fundamentally different. But on the other hand, if you use intersection, and it doesn't really matter. And the order doesn't really matter, so that you can actually write the intersection of them all together. So this operator means can take any number of components or arguments. And this operator, on the other hand, can only take exactly two of them by definition. Other than that, everything else should be straightforward. You can take a look by yourself. And then now you see we can apply that idea into set we introduced before. What if, well, yeah, we know a term is not necessarily a set in general, but what if it is? Then we have some special treatment. You see that a set with multiple components can be defined exactly using the intersections. Okay, so you see that this is nothing but all of those union together or using the what we call intentional intersection operator. And symmetrically, this is all of those combined together use extensional intersection. Okay. think about intuitive, it means the set of things that have all of those properties. Then that can be obtained by take each property and define a set, then take the common subset of all of them, which will have all the properties, and so on. So I have some examples. You can take a look. So this is the grammar. And this here we extend this inheritance logic from layer 2 now to layer 3 by introducing now a term. You see, previously we already say a term can be another term within a set, but here you see, if you're familiar with this grammar notation, you will see this plus means it can contain more than one component in a set. In layer 2, you can only contain one. Here, it can be any number. The same thing for the intentional set. And also, you can take the extensional intersection, extensional difference, and intentional difference. They're defined perfectly symmetric to each other, which I'm not going to repeat. And how about the inference? What kind of inference rules we need to introduce? Now, if we are talking about the non-axiomatic version where everything is a matter of degree, okay? There are a couple of rules involved. First, the choice rule is actually modified. The choice rule we introduced in first layer, which is, I hope you remember, is the rule if there is more than one answer to a question, which one you pick, right? I mentioned that depending on the type of problem, it can either pick the one with the highest confidence or the one with the highest expectation value. Okay? And here we still do the same, but we introduce one more component, one more factor to be taken into consideration. That's the simplicity. Okay? So if there are more than one answers, the choice rule not only will check on the expectation, will also take the complexity. Here we mean the syntactic complexity into consideration, which will use this formula. And then there is a discussion about why simplicity should be taken into consideration. If you try example, you will see later, sometimes the system will prefer an answer which is maybe less accurate in terms of expectation, but much simpler. Okay? Then the system may take that one. Compared with something much more complicated, but just only slightly better in terms of truth value. Okay? So that's one situation. And another, actually, the major part is this part, is what I call the composition rule. That is this. If this is the case, and both of them each of true to a degree, then how to combine these two together into various forms allowed? You see, well, actually I should just use this table. That's the picture I draw. If M is in T1 and T2, or in a common extension, two different degrees, what can you say for the degree of M to be in the, the four compound we just defined? Okay? You'll see that there are actually three functions. Because the last two actually use the same function, you just switch the order, who is number one, who is number two. Okay. The others they have different logical relationship. The basic idea is the same as we have said before. Concentrate on the binary case first. Okay? You see, in this situation, actually, it's pretty simple. For intersection, the binary case, this is just the end. And this one is just the or. Okay? And then this one is the and, but you take the negation of the second component. So that on the other hand, confidence value is nothing but the end of both of the confidence of the premises. So that's actually not the first version of truth value function I use, but I use something more complicated in previous years. Later I realized that there are some situations should be handled in different rules. So in this rule, actually the result can be pretty simple, just like that. So we have examples. So that's the major rule introduced in the third layer. Yeah, too bad we have really limited time. So instead of go through the examples, I will point you to here. You see at the end of my lecture notes, I have links to the examples of each layer. That's the one that actually tested in the current version of the system. You see for each type of the rules of the inference. So this is for second layer. The one we just talked about is the third layer. You'll see that if you know it's a swimmer, it's a type of bird, you'll see the result. This operator is this in a book, okay? This operator is this in the book, and so on. I believe I have a table somewhere to tell you which is which, just because the ASCII version in the demo, of course, cannot match perfectly with the printed version in the book. But very often you can guess this kind of like come from the C or Java tradition, which operator is and, which operation is or. Also you can check the truth value. And this also tell you see basic set operations, and you can see the conclusion, and so on, which we don't have the time to repeat here. Okay, let's take a break to 10:15, then we will go to layer 4. What I call the relational terms. This one, actually, this is one of the simplest layer, even though it related to several important traditional problems. I said at the very beginning, my NAL system and also the IL system within it as a special case both belong to term logic tradition. Okay? I told you that one important property of term logic in terms of representation is to use subject-predicate format. Okay? On the other hand, currently the dominating predicate calculus tradition use predicate name followed by argument list. Okay, is the form of the simplest atomic proposition. Okay? And so this is like Aristotle's logic, and this is like modern mathematical logic. If you pick a typical textbook, it will tell you this one is better than this. Okay? Why? Since it sounds like this, because one common criticism toward this, toward including Aristotle's logic, is it's too limited. You see, it can only have two terms in it. And also it has to be inheritance relation, even though in Aristotle's work it's not called inheritance, but it's still this kind of thing. Okay? On the other hand, you see, in this format, you can have any number of arguments. And also, you can have any relation. Okay? And this is kind of like just a special case, right? So you can easily say that I can use inheritance SP in this format to represent this. But on the other hand, you cannot represent this. Okay? So it's easy to say, oh, indeed, this is better. But it's not that simple. In one sense, this one is indeed limited. But on the other sense, it's very important to see that here, inheritance relation playing a very special role. You have already seen that all the inference rules are directly defined because of the property of this relation. Okay? If you do it in this way, if you make it just like an ordinary predicate, you don't have that special treatment anymore. Okay? Instead in propositional logic or predicate logic, all the inference, as I said before, is pure truth functional. On the other hand, this one related on the transitivity of the inheritance relation. That's a key difference between the two families. Okay? Which we have already seen this transitivity have very special power in terms of inference. Actually, later in AI, when doing knowledge representation, if you pick a AI textbook, check the knowledge representation, you will see that they are already kind of from practice, they already realize this kind of thing needs special treatment. That is the so-called is a relation in many AI representation framework. They gave this one a special treatment compared to everything else. Okay. Here, I say, yeah, that's good, but they're not going far enough. Actually, here, this is nothing but this, but more kind of formal version, and I'm actually put it at the very foundation, and I tell you that's what Aristotle's coupler is all about. Okay. For example, declarative logic. Okay, they're using this as kind of like a backbone, and also, but they still try to do it in this framework. But even though, hopefully you can see that there's some value in this, but still the old challenge is still there. That is, even if you do this, well, how can you represent something like that? What if the relation you want to represent is not inheritance? Okay? What if you have more than two arguments to relate to each other? 3, 4, 5, well, you will have to do that. Okay? For example, I say this computer is on this table or disk. This on relation clearly is not inheritance, right? It's something else. How to do that? Actually, no surprise, the answer has been there all the time. I'm surprised many people haven't seen that. Once again, it's in set theory. Okay? In set theory, how to represent this? Well, right? Where actually, by definition, a set, a relation is a set in set theory. It's just the elements are not individuals, but tuples. It's just that several things related to each other is taken to be an element of this relation. You see here, the game we played is we are going to turn this kind of thing exactly into this. This is a subject-predicate relationship. Okay? And this is nothing we have already seen intuitively speaking. That's a copular. The only thing you need to allow is for the subject to be a compound, which is, something put together one after another as some kind of tuple with a special order, which is, of course, can be allowed. That's not a problem. As soon as we begin to allow compound term. Okay? Then as soon as you realize that, then you see no problem. Whatever you can write in this format, I can just write that, and which is nothing but this, right? Which is nothing but this. What's the big deal? And then after that, I can apply all the rules I defined before: deduction, induction, abduction, blah, 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 on that kind of representation. And I will just kind of like translate term logic, predicate logic expressions into term logic statements. Okay, so that's basically what this chapter is all about. It can be done, easily done. So you cannot criticize term logic on that base anymore. So the only thing you can criticize is the special type of term logic, like in Aristotle's case, where it's assumed the subject and predicate can be a single name, has to be a single name. As far as you gave up on that, you allow structure. We don't have any problem. So, so here, you see, kind of like use the idea of set theory, but not exactly as in set theory, because we do have special requirement here. So that all the following definition is something like that. So first, I define a product, which is typically called Cartesian product in set theory, but it's the same thing. It's kind of like this structure. You put something into a sequence, and usually you assume the order matters. And you see, in this case, you can either write it in this way, or you can write it in this way. It doesn't really matter. It's, this is prefix, this is infix. Okay. Anyway, you're using an operator to combine a bunch of things together into one single term. So, and also you will see that the inheritance relation is kept in a sense. In one sense, intuitively speaking, is this. If you have inheritance relation, say this is P1, S1, P2, S2, P3, S3, blah, blah, blah. Of course, it is not limited to 3. It can be 2 or 1 doesn't make sense later, we'll see. Any number other than bigger than 2 will make sense. If that's the situation, okay, this will also be the situation. Think about that and try to find some example to see what's the intuitive meaning. That's what this means, and also the other way around. Okay. If this is the situation, then for each individual, you can also build that relationship. Again, we don't have the time for all those technical detail, but that's the idea.
Could you give us a very simple example?
Yeah, I do. I do. Yeah. Let me quickly go through a couple of concepts, because in that example, there are several things related to each other. So I have to introduce all the concepts first. Okay. So anyway, this is what I call a product. Okay. Then a related. Yeah, let's first see this group of examples. Each of them is talking about a relationship, and also, yeah, this is called a product. What is a relation? In this system, a relation is any term that can have an inheritance relation with a product. For example, if you have something like this, you have that, you have this, then this is called a relation. Okay, and also if you have this is called a relation. Okay. A relation can be a compound, it can be simple, but it can need to be related to a product. Let's see this example. Once again, on purposely, I'm picking mass nouns which are not sets. Okay? Say, water dissolves salt. Then, intuitively speaking, is talking about the relation between water and salt, which is called dissolves. Yeah. Then, well, clearly this is not the inheritance relation. We are not saying water is a type of salt, of course not. But it can be read in this format. Okay, intuitively it means there is a relation between water and salt. That's what this thing intuitively means. Okay, so these two things can be related, and then their relation is a special case of what we call dissolve. Think about that.
Does salt dissolves water in this case, in this example? What about this?
You just switch here. It's basically the order matters. Which is a pure conventional. Okay. If you always do it the other way around, that's also fine. It's just you need to be consistent whenever you're using a term. So the first place argument and the second place argument need to play the same role. But here I don't mention that role. Okay. For those of you who are familiar with knowledge representation in artificial intelligence, you will see that there are actually many other approaches which is doing the same thing. But a key difference is they take each, for example, if you have this case. They force you to give each position a name. For example, they say the first one is the agent, the second one is the object or a tool or instrument. I understand that the idea is just like what you said. You cannot easily, freely switch the order. Okay, but on the other hand, to me, it's very unrealistic to assume each of the slot or position can be named always in a meaningful way. Okay, so instead of using that, I purely using the relative order to separate them. And later we'll see we can specify their semantic meaning just based on who is first, who is second. So in this case, you can say that whenever I say dissolve, I always mean the first thing dissolve the second thing. Or you can say whenever I use that term, I always mean the second thing dissolve the first thing. Okay, even that's kind of like unnatural. But if within the system you always do it that way, it doesn't really matter. It's just you cannot just do it sometimes in this way, sometimes in the other way.
And as 1, as 2, and 3, it is concepts, right?
Mm-hmm.
And what about relations? Are they concepts too? P1, P2, P3, or not?
P1, P2, P3 in where? Here? Yes, they're all concepts. You see, in this system, subject and predicate is perfectly symmetric. Okay, whatever you can do it here, you can do it here. So you'll see in this case, dissolve appear as the predicate and the product appear as the subject. But you can have another situation where the single term is the subject. You can also say dissolve is a relation between liquid and solid. Okay, here in the predicate, you're talking about kind of like various type of relations between liquid and solid, and you say dissolve is one of them. Okay, and this is also another way to specify kind of like the slot in this relation. You see in this case, the first one is always a liquid, the second one is a solid, so it always means to use the first one to kind of dissolve the second one. You can use this kind of representation to capture or to specify what each kind of the slot means, but you don't have to define them in the very first place. Here the difference is you can have more than one of such descriptions for the relation. Okay, each of them capture, for example, some of the property, okay, or some of the situation. So if you really do a kind of frame-based or slot value-based representation, you're forced to define each slot in advance, which is very limited, only work in well-defined situations. Okay, this one is much more flexible. Anyway, so this is an example. And now this section is about a brief summary of the conceptual relation. Now you can see what we can represent in Nars, which later will remain to be the case. So this not only applies to layer 4, it applies to the whole system, but this only appears in layer 4. That is, Now we know that the knowledge representation of Nars, as I said several times, is a conceptual network, right? You have concepts as nodes and have relations, but what kind of relation? Now it becomes more clear. Okay. At the very beginning, we just talked about, copular. Now you see it's much more complicated than that. Okay. Roughly speaking, there are 3 types of relations. One is what we call syntactic relation. That is a pure format, okay, just because of the name, or literally speaking, what's the relation? Which is the relation between a compound and its components. For example, just in that sense, yellow bird is related to yellow and related to bird, right? Well, of course, it's just by its name, okay. But in what form, in terms of semantics, we don't care. We just say syntactically, the phrase or the compound yellow bird consists of yellow and bird. Okay, so that's what we call a syntactic relation. Or you see, what is this? Ravens, but not black, right? Or non-black ravens. And this thing, from a pure syntactic point of view, is related to raven and related to black, of course. So that's what I call a syntactic relation. Then there is semantic relation. That's the relation represented by the copulars. Not only this one, but also the others that we introduced. Okay? We call it semantic relation because they always say that the subject and the predicate are related in meaning. Once again, we already defined the meaning to be extension and intention, right? So you'll see, they basically say that these two have something in common in extension or intention or both, and to a certain degree. That's what semantic relation means. Okay, what makes this one different is in semantic relation is always 2 things. You always directly relate 2 things to each other. Even though one of the things can be a compound by itself. Okay, and also there is a limited number of semantic relations. As I said, in implementation, actually there are only 4 of them. It's very limited. Also, the syntactic relation, of course, is also limited by what kind of operator you allow. Okay? There is a fixed number of operators, but there is much more than 4. Okay? We have actually, I already showed you in a grammar, which is, I think is around 15, something like that. I never count that. But anyway, it's less than 20, more than 10, I believe. Okay, which will include something like, you see this, and this, and this, and this, and this, and later we are going to introduce a bunch of others. But it's fixed. Okay? And finally, there is a so-called acquired relation, which is things like dissolve, on top of, beside, say, brother of, that kind of thing. Okay? That's unlimited. It's not built in. It's something the system learns from its experience. It's not directly handled by the inference rules. So I don't have a deduction rule just work on brother of. Okay, there is no such a thing. But I do have a deduction rule which work on this. I also have some other rules work on this and this and this. Okay, so you'll see that the first 2 types of relations are built in the logic, into the logic. It's part of it. And then everything else is handled in the way I just introduced. You design a concept, I treat that concept as a relation, and then like in set theory. And the meaning of that relation is determined just like the meaning of all the other relations, that is by its relationship with the other terms. On the other hand, the meaning of this and the meaning of this are fixed. It's kind of like the system was born with an understanding about what those things mean. Okay? But with no knowledge about all the other relations which will be learned from the experience. That distinction is very important. You see, every logic, especially the one used in AI, is facing a decision about what to be built in, what to be learned. Okay, that decision is crucial. You cannot say, I want to learn everything, but you cannot start from nothing. Okay, you have to build something into the system. On the other hand, if you build too many things into the system, like conventional AI, okay, you cannot learn much. You basically depend on your built-in capability, which also is trouble. Okay? So you see, my decision here is I say syntactic, semantic, they're built in. Everything else, I just call it acquired, meaning that it will have to be learned. So,
syntactic and semantic relations are structurally different, aren't they?
Yeah, they are completely different.
And semantic and acquired relations are structurally identical, but they differ in source.
They are also, I will say, fundamentally different. Because you see, if you check the inference rules, the inference rule only directly recognize things like this and this. There are constant symbols in the inference rules. Or if you go to the grammar of the system, you see that only those things appear in the grammar. Everything will be, say, behind a term. We have a variable which is a term which can be anything. Okay, so all the other relations will be that kind of term. You can call it relational term, but it's kind of like have to be learned from the experience. Again, we need more example, I know, but we are not there yet. Okay, this is the last thing I want to mention. Then we're going to see examples. Image. The basic idea is already there, but we still have trouble by, you'll see, by doing this format. Okay, let's see. If there is a relation between A, B, C, which is called P, well, we can write that in that way. And then this is a compound, this is a term. AI semantically, or in terms of meaning, that's good enough. But in terms of inference, it's not good enough. Why? Because this is a compound. Okay, this is according to what we have learned. We are going to take this as one whole thing by the inference rules. And this, of course, will be taken as another term. The problem about that is some of the inference, you see, let's see this example. Once again, we see water dissolve salt. We say the relation between water and salt is a special case of dissolve, which makes sense. But some inference we want to make will take this and this or this as the common term. Okay? For example, if this is the one premise and another premise is, say, D is a special type of B. Okay, like in this case. Water dissolves salt, and rain or rainwater is a special type of water. Intuitively, we want to get the conclusion that rainwater or rain dissolves salt by deduction, right? It should. But the deduction rule doesn't apply. Okay? Because the deduction rule requires the format, you know this. Where you need to kind of like isolate the concept in both premise by itself, so it can become the medium of this transitivity. Where here, you know, this guy is here, this guy is here. It doesn't fit into that pattern. So here, when I design a system, I have actually two choices. One choice is to rewrite this sentence in a certain way so that B becomes the subject. Then it becomes, you know, the same old rule. So you need to add some kind of translation rule. That's one choice. Another choice is to do inference as it is, but to define another version of deduction. See, that deduction will allow this and this to be premise, and then from them, I will directly say that from them I'm going to derive truth value function should be the same. Okay? And after some consideration, I think actually the other way is easier than this way. Later I will give you more and more evidence to support that. So the basic idea is what? Okay, now I want to represent the same thing, but with B as the subject. Okay? So that's what the whole intuition behind this whole the thing called image. Again, the basic idea comes from set theory. Set theory have something similar, but not exactly the same. Okay? You see, basically, again, let's start with a simple situation where you have only two things. Okay? Then in set theory, you can somehow talking about the image of A under P, or the image of B under P. That is kind of like P, you see it as a mapping. Okay? Then you can say A is mapping to what under P, or who what kind of thing have the relation P with A. Or you can ask the same thing slightly differently about what kind of thing have a relation with B, which belong to the P relation. And also you have to somehow distinguish their relative position because the order matters in this case. Okay? So that's the intuition behind this one. The representation looks a little bit confusing, but after you get used to it, actually it's not too bad. Okay? So see, that's exactly what I have here. If you have a relation R and a product T1, T2, then first we talk about the extensional image, which is kind of like what I'm discussing here. And symmetrically, of course, there is also an intentional image, which is defined in this way. This one is equivalent by definition to this one. Here you see the first is the operator. Okay? I use this one because intuitively speaking, product is multiplication, right? So that the reverse is division. So I'm using that operator because of that reason. Okay? So you can say that, and the second operator, the second one is a term which should be the relationship itself. Okay? Then after that, you have this one. And this is a special symbol. In the implementation, it's underscore because you don't have a diamond key, right? It's basically indicate if you put this thing back into the relationship, whether it's which place it is in. Okay, so see, it is here for this one. It's here for this one. Just a placeholder to keep the order. Okay? So what's the intuitive meaning? Let's see this one. This concrete example. The same sentence now can be rewrite in this format and in this format. And the intuitive meaning is what is water belongs to, or water is a special case of whatever dissolves salt. And also similarly, salt is a special case of whatever can be dissolved by water. In natural language, no matter which language, okay, this kind of representational structure always exists, right? Just in different form. Okay, so it's basically you define a concept or you specify a concept by its relationship with other concepts. So, well, how to write that in a formal language is, well, it's up to you, but that kind of thing need to be able to be specified. So you see, as soon as you allow that kind of rewriting, you see, this three will have the same meaning in the sense that they have the same truth value. If you believe one to a degree, you should believe the other because it's basically the same sentence. Just like in natural language, like kind of passive voice and active voice, you put different thing in the place of the subject, even though you're talking about the same thing. with a slightly different focus. Okay. So the good thing about this is as soon as you allow that kind of thing, you don't need to do anything about the inference rule anymore. Okay. You see, I rewrite this into this format. And this format will naturally be used as rain as a type of water to derive rain dissolved salt. Okay? Just like this. And this one, using the same format, can be rewrite back into this format and this format. You can say that there is a relation between from rain to salt, which is a special case of dissolve, or you can say salt is something can be dissolved by rain. Okay.
Is the diamond a popular, or is it a...
A diamond is a special symbol. It's not anything we have introduced. It's just a placeholder or an indicator. Okay. You see clearly here, if you don't have that, then it's messed up. You don't know whether it's water dissolved salt or it's salt dissolved water. You have to somehow keep an order.
So it's kind of like a lambda function.
Yeah. You can also think it that way. Actually, there is more than one choice to do this. It's just as far, or you can use a number, right? You say this is a number one index, or this is a number one component. This is a number two. Actually, in the implementation, I'm using an index value, an integer, to indicate, if this thing is going back into the relation of which position it should be. And also, it can be naturally extended into a structure with more than two components. You can clearly see there's no problem. Okay, just a little bit more complicated. Now, I think I'm ready to talk about the inference rules. All the formal thing we can skip. Now is the new grammar rule. You see, for layer 4, the new grammar rule is just we allow a product or an image to be used as a term. That's all. Actually, there is no inference rule in the sense of there is no new truth value functions involved. Okay, the new inference rule is kind of like a rewriting or translation rule, which will allow the same thing to be written in different way. As we will see, in the example. And this, I think, the best way to see is check out the examples. Also, you see this asterisk is the ASCII version of product. So this sentence say that, this is a rough English translation. Okay, acid and the base can have a reaction. So we are talking about a relationship, which is a special case or whatever we call a reaction. Okay, and also you see the system has rules to do what we call structural transformation. It's just equivalent rewriting. Okay, if you put this sentence into the system without mentioning anything else, the system after a while will automatically rewrite it in the other two format with the same truth value. You see, that's the default truth value of the system. Okay, the system will say, I think that means acid can react with base, and base is something that can have reaction with acid. Of course, the English translation is not means to be unique or accurate, but more or less it captures the meaning. And also, you see, if you give it the other way around, if you start with an image, then it can give you the product version and also the other image version. It's kind of like you see you're moving this into the structure, you're moving this out of the structure, and also, of course, this placeholder now is in a different position. Okay? But it's not really difficult to do. So structural transformation, and this is something exactly the same thing, but not there. Here, this is just the other one. You just use the second one. This is the same thing the other way around. Now you see the compound become the predicate, and then what you get is this image, the backslash version. That's what I call intentional image. Okay? So if you read the English translations, you will see what they mean. It's basically the same thing, but the other way. So also there are some relation, some special inference rules which applies to this kind of structure. For example, if you know bird is a kind of animal, and then the relationship between bird and the plant is a special case of the relationship between animal and plant. That here the truth value function actually is deduction. And a couple of others. Okay, not too many. Relatively speaking, this layer is relatively simple. But because of this translation, as I mentioned before, after you do rewriting, okay, you can use the inference rule we have defined before to combine things. That is what I have said more than once. That is, this layer thing is just conceptually introduced when I designed the system. The actual implementation, everything is actually mixed together. Okay, so that you can use this with the layer 3 thing, so that you can have a compound which contains structure and so on, product or image. You can use it with the layer 1 inference rules to do deduction, induction, abduction, and so on. They're all allowed. Any kind of combination will be allowed by the system. So that's kind of like the technical content of layer 2 to 4. Okay? But there are several important conceptual issues I want to discuss, which is not explained in detail in the book, but I write 2 sessions in the lecture note, which I want to explain the rest of the time. You see that I think everyone already knows this. A central issue in cognitive science and AI is how to capture the meaning of a concept. Okay. Think about it. In traditional or mainstream approach, how do you capture the meaning of a concept? I will say that the dominating approach fell into 2 categories. One comes basically from the logic tradition that basically say that meaning of a term is denotation, is what it names in the world or in a model, okay? Which I already explained before when we talk about the experience-grounded semantics, to say why that's not what I'm using here. Another approach in this discussion is more often used in AI, is to think the meaning of a term is determined by a definition. That's also something we run into in everyday life. Okay, when you want to know what do you mean by a certain thing, you typically ask the other guy, give me your definition of that concept. And many people even believe that in scientific study, if you don't have a definition, that thing is meaningless. Clearly, there are tools or foundations behind both of the 2 approaches. But there is one thing in common which makes both of them bad for cognitive science and AI, especially AGI. That is because, according to both of them, the meaning of a concept is a fixed thing. You see, I already mentioned from the very beginning that the attitude I have in this approach is exactly the opposite. That is meaning change over time. But on the other hand, it's not arbitrary. It doesn't mean whatever you want it to mean, or arbitrarily or whatever. Okay, it's still grounded or determined by what? By the system's experience. Okay, so you'll see here, this in a sense is a third way to introduce the meaning of a concept is by relation. Okay. So what bird means, well, is how bird is related to the other things. And where the relation come from the system's experience, right? Some of them are given, some of them are derived from the given. Okay? Even this idea is not really new. Many people have mentioned something like this. Okay? But for this kind of definition, there are always this kind of way to capture meaning. There are always criticisms. Common criticism, I will say that there are 2 of them. One is, say, this definition is way too holistic, meaning that if you say it depends on its relation with other terms, well, everything is related to everything else. Well, I have already mentioned that, right? If I push it hard enough, you can really make bird related to any arbitrary concept, somehow. So how can you handle that? That's clearly not allowed especially in AI, right? When you really try to implement something. For me, actually, I have already explained to you last time how I handle this. Because you see, in this situation, resource restriction actually become a good thing. Yeah, in reality, bird is related to 1 million other things. But currently, you only have the time to take 5 of them into consideration. Which 5 depend on the priority distribution, blah, 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 right? So that we can still allow this definition without arbitrarily introduced complexity. Okay? So that's one thing. Another criticism will say, okay, even if that's the case, then it seems your definition is pure subjective. Okay? What if your experience about bird is different from my experience of bird? Well, actually, it's not really what if. It has to be the case. Okay? Our experience about anything between any two people will always be different. There's no way for it to be identical. So that people can easily say, okay, your definition is way too subjective. Okay? So my answer to that is yes and no. Fundamentally, yes is subjective by definition. Okay, my bird is different from your bird. But on the other hand, as far as we live in the same environment, as far as we begin to communicate with each other, okay, that communication and the shared experience, both physical experience and social experience, will begin to play a bigger and bigger and bigger role in the meaning of a concept. So eventually, I guess you all have this experience. Between you and a friend who share a lot of experience with you, you tend to use the same word to mean the same thing. Okay? Between you and someone who comes from a very different background, communication and mutual understanding become harder and harder. Okay, that can be naturally explained by this model of conceptualization. That is because, well, understanding or agreement is always a matter of degree. It's not a yes-no issue. Okay? So this is related to the issue that whether we can really understand AI or whether AI can really understand us. You see, according to this, you can guess my answer is it's a matter of degree. I don't think AI will perfectly understand us, even though I believe AGI is possible. That's two different issues. Okay, I cannot say because computer not completely agree with me about what bird means. It's stupid. Okay, it's different from me. Well, that's clearly not because the computer can say the same thing. Because well, I'm stupid because I'm different from the computer. And we have already seen a lot of this kind of thing in human history. You know, some people judge other people's intelligence just because you know whether you agree with me or not. Okay. Here we can explain whether you know you can have more than one system or several systems which are equally intelligent, but have a lot of disagree on many things. Why? Because they don't have the same experience, and they haven't communicated long enough. You see, communication will provide the tool for your experience to become part of my experience. Okay, so you know, communication is usually always good if you can afford the time. In terms of remove disagreement, but still, don't expect everyone else to fully understand you. According to this model, that's impossible. Okay? But still, well, usually you don't really need that for you to live in a certain community or to work with other people. So that is one thing. Another thing is this can naturally explain both how meaning change on one hand, on the other hand, why it's not changed completely arbitrarily. Okay? You see that every new experience about a concept will more or less change its meaning. And also we see, as I said before, in different contexts, you may focus on different aspects of the same concept, which explains why meaning is context dependent. Okay? Well, this is a phenomenon that everyone have agreed in AI and community, just people have different approach to capture that in the system. Okay? For example, a common approach in AI is just to introduce some kind of thing called context as another parameter. Okay? So you see the same concept in context T1, that's one meaning. The same context in context T2, the same concept in context T2 is a different meaning. Well, intuitively speaking, I agree, but what I don't agree is I don't think you can clearly separate the context one by giving each of them a name. In this system, context actually is everything around you. Okay? So actually, I believe my current lecture already created a context for you guys around your notion of, say, meaning, a bird in your mind to a certain degree. Okay? But we cannot really give each moment in this discussion a different name, so that's a different context. I use that in the inference process. It's not going to work. Okay? You just need to allow for it to be fluid, to change over time, but on the other hand, you see it's clearly not arbitrary at all. Okay? In what situation, which link will be brought into consideration, we have already explained, depend on many factors.
But bird in a park and bird as a dish, they are in different contexts, but for your system, they will be different concepts, different terms.
Good question. It can be both. It can either be, say, bird with different relations activated, say park. Okay, so when you're talking about a bird in a park, then this relation will become activated, and when you're talking about bird. And then the restaurant in a dish, that's a different story, so you pick different thing. So that's one possibility. Another possibility, yes, as you said, you can introduce another concept and just like intuitively say, okay, so somehow we can translate this into a compound. Using, for example, in as a relation we introduced in layer 4, that kind of thing, and then that compound will become another concept which is semantically related to bird as a kind of special case.
So contexts are very implicit.
Yes. So in this case, context will be explicit in the name. In this case, context will be implicit in priority distribution. Okay, I will say in general, both of them are allowed. If you want to make it very clear, you do it. You just introduce a new phrase. But this is more general. Okay, and also sometimes you don't really have a name for that special thing. You're still using an old name, but in a special way.
Thank you.
Okay. Any other question? This is a crucial issue. Okay, of the whole model. It's a very important issue. Let's see what else. So you see, I believe this is a very simple structure or very simple model, but it explains many things in the history of AI and cognitive science. Okay. And also, you see, I already mentioned, even though that each time when you talk about bird, you pick something randomly with a different priority, but I also mentioned in the long run, okay, there will be a priority distribution. And some of them become stable. Okay? For example, for bird, again, in theory, there is a meaning relation. Not only in theory, maybe in the implementation, in that data structure, this node or this term is actually related to 3,000 other terms. Okay? But only, for example, 10 of them have high priority. And also high durability, meaning that whenever you're talking about bird, I almost always think about those 10. Everything else, well, I just occasionally think about this or that. That explains what we call something called what's the essence of a concept or definition. Okay, what's the definition? To me, a definition is just a couple of links which is essential to a certain concept, and also everything else almost can be derived from those things. So yes, in my system, I can allow some concept to have definition. But what I'm saying is not every of them. Some terms, we don't really have any reliable core relationship. It's much more flexible. Okay? So for those kind of things, they will relate to other things like prototype or say family resemblance, blah, 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 whatever you call it. Okay? But some others, yeah, there is a definition, roughly speaking, meaning that, as far as you remember this three, everything else can be derived. But it's not always that like that. But I'm not saying it's never like that. Okay? So, yeah. So in this sense, definition becomes a special case. How about denotation? To me, that's also a special case. That is, if one of them later in layer 8, we are going to introduce the concept that some of them is not really a word, some of the concept. It can be a sensation or perception. Okay, some kind of mental image. Then if a concept is fully determined or mostly determined by a strong link with a certain mental image, then that thing is kind of like more like defined by that picture, which is also possible. But clearly not universal in the system. It's not everything have to be defined in that way. Okay, that's also related to so-called symbol grounding problem. Okay. For some of the concept, yes, the meaning mostly come from sensory motor. For example, verbs. Say push. Okay, push is basically this. Okay, it's an action. But it's still related to the other concepts more or less. Even though this relation, that is the word, related to certain kind of muscle movement, play a central role in it. Okay? But if you push this concept too far away, say everything has to get its meaning from sensory motor, that's clearly not right. Okay? It's a highly specialized situation, which actually applies to my analysis of many other psychological model of concepts. Okay? Each of them, you see the psychological experiments to support that model. Yes, I agree with all of them. But each of them capture a special case. Okay? For example, some psychologists claim, the meaning of a concept is basically defined by examples. Yeah, you can find cases for those things, but not for all of them. Some people say it's, the meaning of a concept is related to or determined or defined by the causal relations related to that concept. Again, that's a special case. Okay. Here we just say it's determined by conceptual relation. What kind of conceptual relation? Well, it can be any of the three types. It can be syntactic, semantic, or acquired. And also, it can be extensional. It can be intentional. It can be sensory motor. Okay, but each of them is a special case. In general, you cannot say it's always like that. So another example is this. That's a well-known thing in psychology, which is related to what I just mentioned, Tversky and Kahneman's work. Okay, let's read this. There is a description about a certain lady called Linda. Then we can ignore the detail, okay? The interesting thing is then they ask subjects of their psychological experiments 2 questions. Which is more probable? Whether Linda is a bank teller is more likely to be the case, or Linda is a bank teller and is active in the feminist movement. Actually, they pick the description about that person to, you see clearly, match people's prototype about women that are active in that movement. Okay, most people will say it's the second one, which is more likely to be the case. But from a pure mathematical point of view, that clearly cannot be right, because the first one, no matter what, okay, you say is position P. The second one is P and Q. Okay, it's impossible for this to be more likely than this. Because it's kind of like this, depends on one condition, this one depends on 2 conditions. You add a second condition, you always make it less likely to be the case. If we are talking about the probability of that thing to be true. Okay? This is why it's called, this is conjunction, right? That's why it's called conjunction fallacy. That is, people consistently evaluate this kind of situation to say that it's more likely for A and B to be true than for A to be true by itself, which is clearly wrong according to probability theory. Okay? So there is a huge literature on this problem. My solution, actually, according to the description you can guess, is actually pretty straightforward and relatively simple. I say here the key is in traditional model, including probabilistic model, they take a concept to mean exactly by its extension. So what does that mean? That bank teller is defined to be a set, okay? Feminist bank teller, of course, will be a subset. Probability is interpreted pure extensionally. It's kind of like when you throw something into this picture, what's the chance? Is your chance bigger to fall into this or this? Of course, the bigger one is more likely to be the case. Okay? Or you pick a random person. It's much more likely for that person to be here than to be here because this is part of that. That's obvious. But the whole trouble is this picture itself is wrong, according to my model. Okay? That is, we don't evaluate the possibility of someone to belong to a certain category using a random sampling. No, instead, the picture according to my model is something like this. You see, bank teller is a concept. Okay? Feminist bank teller this is not minors, okay? This hyphen. Just to make things simple, I just use a single letter. So this is a concept. This is another concept. Yes, there is an inheritance relation. A feminist bank teller is a bank teller. Okay? But now the interesting thing is when you decide whether Linda belong to this one or belong to this one, how do you evaluate its truth value? According to my model, you will see it can be done in many different ways. Okay? If you do it in a pure extensional point of view, I actually have data to run in Nars to show you this. Okay? If you calculate, for example, this truth value from this truth value and this truth value, okay, then you're taking it in one direction. Or especially if we be more consistent with their model. Okay? If we say that we have a woman as a concept, okay? We know Linda is a woman, and we know what's the percent of women to be bank teller. We also know what's the percent of women to be feminist bank teller, okay? If we do it in this way, clearly the probability for this one will be higher than the probability of this one, according to the statistics, okay? Because that's much less likely to happen among women. But if we are doing it in intentional point of view, that's what this data actually guide us to do. That is, we are going to introduce a whole bunch of properties. Forget about the base rate of women. Okay, we are talking about age, certain age group, marriage status, and whether it's outspoken or conservative or whatever, whether it's bright or not, whether major is in philosophy. What are those? Those are properties. Okay? Then what it guides you to do is you are going to see that this Linda share more property with feminist bank teller than married bank teller. More property means by abduction higher confidence value. We have already seen that. Okay, so if you set up your data in this way, this will have a higher truth value than this. It should be. You have more evidence. Okay, so you see the problem not really because why? It's just simply because this thing is not calculated from this thing. Multiply a certain factor which cannot be bigger than 1 anymore. It's calculated completely from a different path, and that path actually, according to the data, should give you a higher confidence value. Okay? So according to my model, actually, every human being are rational on this problem. Probability theory, especially the previous application of probability theory, is wrong. Why? Because they're using data which is not available, and they're missing the data, or they're ignoring the data which is right there. Okay? Why? Because according to probability, those data doesn't matter. Why? Because a concept is defined merely by its extension. It's a set. Okay? So that's not only in this experiment. Actually, it's in the whole field of human judgment decision making, behind Tversky and Kahneman and many other people's work. Okay? So you see here, the basic issue is, what is the meaning of a concept? If you change that, you change everything. Okay? And there are a bunch of other things also are very interesting, but we hopefully, unfortunately, we don't have the time to talk about. I also have some previous publication on some related things. Again, one of them is called Watson's selection task, which have a similar taste. It's kind of like everyone is doing something, but according to some model, that is wrong. Okay? If you check the existing literature on human rationality, you'll see a lot of psychological experiments say humans are irrational in this flavor. My conclusion is humans are rational. The problem is traditional models are too limited. They only capture special situations. And in all of those things, as far as I can tell, my model fit the human behavior much better. And also, not only I fit the human model, I also explain why that's the right thing to do. It's not like a pure psychological model say, yeah, humans indeed work in this way. You'll see in this model, I tell you, not only indeed human work in this way, AI system should also work in this way. Okay, it's not a fallacy at all. It's sometimes, well, I'm not saying that human doesn't make a mistake, okay? I'm saying this is not a mistake. But there are some mistakes, but even those mistakes, I will say, that's inevitable. Why? Because you don't have the knowledge, you don't have the resource. That's the best thing you can do. And then what you realize later, you realize you're wrong. Well, of course, you just modify your belief accordingly. Okay. So there is a large number of problems in that category which can be reinterpreted according to this model. Also, there's something called basic level categories, which say that, you see, the concept, we have a huge inheritance hierarchy. As I said, you have a bird, and you have animal above it, you have different type of bird. But somehow the concepts in the middle are the one that used most often. Not the most general one, like thing or object, or the most special one, okay? And this type of bird of this kind of color of this kind of size is the thing in the middle, okay? And in this model, you will see that the concept in the middle kind of like, in a sense, best related to everything else. Because when you move up, we already said, you have a bigger and bigger and bigger extension, but you have a smaller and smaller and smaller intention. That is, you cover a lot of things, but you cannot say much about them, all of them. On the other hand, you can be more and more and more detailed, but only about the smaller number of things. Okay, the basic level concept are typically in the one in the middle, which is still cover a lot of things. I can still say a lot of meaningful things about them. So in terms of economic evaluation, in the long run, they will be the most useful one. Okay, that also related to the concept I mentioned last time, talking about the priority. You are going to evaluate the quality of a concept. That's actually another factor I didn't mention. Okay, in this model, the kind of mid-level concepts, that is, both have a rich extension and a rich intention, will be given a higher priority in the long run. Okay. So the last topic I only talk about briefly is another example which support the claim I made at the very beginning in the first day. I said this system is a unified system. Okay, it doesn't have separate modules. Each of them capture a function, then relate to each other. Okay? Here I talk about one example: learning and reasoning. If you pick any AI textbook, you will see typically learning and reasoning are captured in different chapters using different technology. Okay, in Nars, now I think I can make the claim: learning and reasoning, same thing. You see, why? Everything, according to the process I mentioned, is inference, right? So first I will claim everything is reasoning, because all the activity are controlled by the inference rules. Besides the inference rule, basically there's nothing else that will change the system to believe. Okay? The inference rule will allow you to create a new conclusion and modify a conclusion and so on. So everything is reasoning. What is learning? Well, learning is how you change your belief, right? And what is your belief? It's that graphical conceptual network. Okay? How to change that network? Well, basically create new nodes and new links and change their values. Okay? That's learning. So all the learnings are carried out by reasoning on one hand. On the other hand, the function of reasoning is nothing but learning, to change the picture, change the network. There's still a difference between the two, yes. When you talk about reasoning, you typically concentrate on a single step. What's the premise? What's the conclusion? Why you use this truth value function? Blah, 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 blah. When you talk about learning, you typically talk about the long-term consequence or effect of this process. You say, oh, something becomes stronger, something becomes forgotten, blah, 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 blah. So you describe that as a learning process. Okay? What I'm suggesting is there is no learning module and the reasoning module, and they exchange data. There is no such a thing. Okay? It's the same process. You're using two different language or vocabulary to focus on different aspects. Later we'll see. That's not only for this tool. Almost everything else will be handled in this way. That is the same understanding process. Okay. For example, the same thing is categorization, right? There is no separate, module which create concepts, evaluate concepts, and change concepts, and so on, because everything is done by the same thing. But you can still talk about categorization. You can talk about where new concepts come from, how a concept can change its meaning gradually, how the meaning of a concept depends on the context of the system. You can talk about that. You're basically selectively talking about one aspect of the understanding process. So the strong argument I want to make on that is, just because in psychology we have a special topic, it doesn't mean you have an independent process which is responsible only for that topic. Okay? Even though many AI systems, according to my opinion, is built their design architecture based on those kind of assumptions, just because, there's such a topic, we must have such a module which is doing that. Then we think about how it's related to other modules. Okay? I can see where the idea comes from, but in many of the situations, that actually doesn't lead to the best design. I'm not saying that's impossible. Okay? Probably not a good idea. So that's basically what I want to talk about today. And you see, tomorrow will be different. I treat a session with Chris because of their schedule problem. So tomorrow I'm going to talk about a whole day. Okay, morning is me, afternoon me again, and I'm going to finish the whole thing. And then Wednesday they are going to use the whole day, okay, to finish their course. Then after that, Thursday, Bengozo and his team will show up. Anyway, the last thing I want to mention is this evening I'm going to have another office hour in the classroom I mentioned before. By the way, last time some people cannot find it because it's a little bit confusing. It's not the second classroom building or classroom building number 2. That's something else. Okay, it's called the science building number 2. It's just right by the east gate. And also the room number, well, actually there are 2 different versions, and both of them make sense. It's either called 103, that's the first floor, the third one. Also, it's called 2103 because this is the building number. Okay, so that's also causes some confusion. But anyway, if you want to be there, if you want to talk about more about this, I probably will be there. I will be there probably between 7 and 9 this evening. Okay. I hope tomorrow I'm going to schedule another office hour. That will probably be the last one. Then I will leave the room for the other instructors to use. Okay, that's all for today.